Okay, dear students, we will try to understand some of the basic concepts of NMR spectroscopy. And then what is NMR? NMR, the abbreviation of NMR is nuclear magnetic resonance, and it is the spectroscopy that deals with the radio frequency. It absorbs the radio frequency, and then the matter, when it absorbs the radio frequency, certain changes happens, and then we'll try to probe those changes. By probing those changes, we'll try to extract some information. Especially the organic spectroscopy has a lot of significance in NMR. And then these are some of the major applications. If you want, if anybody is interested, maybe you can go through all those things. So majorly, as a chemist, we will be focusing on the first point, that is the structure elucidation. So natural product chemistry, synthetic organic chemistry mainly depends upon NMR and mass spectrometry. And the study of dynamic processes can be studied by the NMR spectroscopy. In fact, it is one of the major research area by many of the biophysicists. If they want to study the protein folding and unfolding movements, then NMR spectroscopy allows gives certain time scale information from which they used to extract some events that happens at the microscale level. A complex structural illustration of complex molecules. Complex molecules means biomolecules like proteins and peptides. These are the molecular weight of those molecules is much higher and very difficult to get the structure of those compounds. However, there are two major techniques are there to determine the exact structure of bigger molecules. I mean, proteins and peptides. Of course, peptide is a small amino acid molecule. I mean, a series of roughly about 10 to 15 amino acids. If they if they are basically arranged in a series fashion, then we will have a peptide. Many of such kind of peptides are basically form proteins, which is much bigger than the peptide. So determining the structure of proteins and peptides are very, very important. Not only the structure of a molecule is very much important in various fields. You take it to any field, it has got its own significance. In that context, the determination of the biomolecules structure is very important, especially in the drug designing. If you want to design a perfect drug, and if you know the exact structure of protein and peptides, then it is fairly easy to design a very good drug for the disease, whatever you target it. Right? So that is the three-dimensional information is nothing but the structure of a molecule can be obtained majorly by two techniques as of now. Those are X-ray diffraction techniques and also the NMR technique. Of course, NMR technique is not widely used, but then as compared to the diffraction technique, but still it has got its own roughly about 5% of the protein structures solved till today. Those are actually based on the NMR techniques. Okay. There are several techniques, several biomolecule structures have been determined by the NMR, right? Of course, the major share and then credit goes to the X-ray diffraction technique, but then NMR has got its own relevance. And metabolomics, and then drug designing, and the clinical diagnosis, that the MRI technique has another major discovery. I would say that it has got its own significance in the clinical diagnosis to find to probe exactly what is happening in the microscale level in a cell. And then this is a brief history, and then it started with the atomic resonance, nuclear resonance, and then it has slowly gone to the molecule nuclear resonance, and then finally it ended with a very beautiful application in the clinical diagnosis like MRI technique. So still this research is very, very active, and these are some of the people who have contributed and then significantly, and they have shown very breakthroughs in the subject, and for which the Nobel Academy has given Nobel Prize to them. This is the person Rabi. So he is the first man actually to develop this atomic nuclear resonance concept, for which he was awarded Nobel Prize. And then these two people, Purcell and then Bloch, Felix Bloch, both of them have actually experimentally determined and then determined measured the resonance, molecular resonance for the first time, for which they were awarded Nobel Prize in 1952. And then the Richard Ernst, so he is in 1991, he was awarded Nobel Prize for his high resolution NMR techniques. Especially, he has introduced the pulse technique, which was considered to be the fastest technique in terms of collecting the data. Traditionally, people, when it was developed, people started using the scanning method, which was actually a cumbersome task, and also it takes a longer times to record an NMR spectrum. However, it was later by the Richard Ernst, and then subsequently by a couple of people have developed a fast NMR technique, fast and high resolution NMR technique, for which he was awarded Nobel Prize in 1991. And this is Othrik. He's from QTH Zurich. He was awarded Nobel Prize in 2002 for his three-dimensional structure determination of macromolecule. If I'm correct, it is I forgot the molecule name, but it is a big molecule. So the protein structure, he was the man actually showed that the NMR can be used as a tool to determine the structure of a complex molecule, for which he was awarded Nobel Prize. And then these two guys were awarded Nobel Prize in 2003 for the MRI technique, which is ultimate diagnostic technique for most of us. I'm sure that you know what is MRI technique. For the doctors, that is a kind of ultimate technique, and it gives you complete nice high resolution images at the microscopic level, which allow the doctors to diagnose the what exactly happens in a particular tissue or area from which they try to give the medicine. And these are some of the resonance peaks which were recorded at the early stages of its developing the NMR spectroscopy. This is a water resonating spectrum recorded in an oscilloscope, where you can find very nice. So these are kind of baseline, and then where you can see a nice peak. The peak means that there is a resonance, and this is something that you may find that for giving this, for recording this, those two people, Felix Bloch and Purcell, they were given Nobel Prize. You know, nowadays it may not be a very great discovery, but those days where there were not much of electronics development, and then semiconducting devices were not there, but still they could record a resonance signal of a molecule, which was actually a breakthrough. So just for recording this one, they were awarded Nobel Prize. I'm sure that nobody will give Nobel Prize for this type of machining, because nowadays people are very crazy. In your seniors who has done the dissertation, they have actually recorded their spectrum much better than what you see here. But still, those days, the discovery, what they have made, a small discovery, was a breakthrough. That is why they were given Nobel Prize. And then these are the, you can see the upper panel, this is the ethanol nuclear magnetic resonance spectrum of ethanol, where you can see, you don't see any splitting pattern, but you will see only three different peaks, which actually gives you an information saying that three different type of nuclei are present. And the modern NMR spectrum of ethanol is just shown down. You can see that this is highly resolved NMR spectrum of ethanol molecule, which is totally different than what you see in the upper panel. Okay, so but this is the older recordings of ethanol spectrum. These are some of the aspects we will try to cover as a part of this physical, the molecular spectroscopy technique, spectroscopy course. And we'll try to understand what is the basic principle and theories behind NMR, and then what is resonance condition, and some basic concepts of the NMR instrumentation, what is the chemical shift, and then we'll try to understand NMR times, NMR scales, and what are the factors that influence the chemical shifts, relaxation dynamics, and then pulse techniques, and then spin splitting, and finally we'll go to the nuclear overhauser effect. As a chemist, we mostly will be interested in two aspects: either if you have a spectrum, if you have a molecule, or if you have a transformation. Let's say you are taking a particular starting material to a product through different processes, I mean through different steps. In each step, you want to confirm that the molecule has formed or not, right? So in that particular aspect, we need to know what would be the chemical shift values, or what would be the NMR spectrum of the molecule which has formed. Unless you have the rough estimate, you can't actually interpret the data, what you got it. So suppose if you have a structure, then how to interpret the data, what you have got it. That is one concept that we will be learning ultimately after going through all the basics. Similarly, if you have a spectrum like this, if you are supplied with the only spectrum, how to solve the puzzle. Okay, how to solve this particular spectrum to the molecule, what is shown in the transparency. I mean, basically, if you are given a spectral data, how to interpret to appropriate structure. On the other hand, if you are given a molecule, how to estimate the NMR data of the compound. These are the two concepts ultimately, as a chemist, that we are interested in. There are other areas. Chemists still use the NMR as the tool to probe it, but at the MSc level, we will try to confine only to these aspects. The basic idea, the basic principle behind NMR technique is basically, certain nuclei actually possess the spin. That is the basic thing. We know the electron spin concept, and the electron spin is very much known to most of us. Okay, the electron actually precesses, so it has got half spin. Okay, plus half and minus half. These things are already known to us. Likewise, certain nuclei in the periodic table also possess the spin. Okay, so their spin quantum number is very much important in NMR spectroscopy, and those nuclei which do not possess the spin, they do not show NMR. So we need not to discuss about that subject. So the NMR spectroscopy deals with the atomic nuclei whose nuclear spin quantum number is non-zero. Now the question arises that we have 110 or 115 elements are there, out of which one is an NMR active and which one is not NMR inactive. What do I mean by NMR active and inactive? A nuclei is said to be NMR active only if it possesses the nuclear spin quantum number which is non-zero. Otherwise, it is said to be inactive. Okay, so now out of the so many elements that we have in the periodic table, if somebody asks you which one actually is NMR active, which one is NMR inactive, then one has to go through the periodic table and then find out what exactly it is. Okay, so there is nuclear periodic table itself. Some of the periodic table, they will mention the spin number also. You have to go to it. On the other hand, there are some kind of thumb rules are available, and the thumb rule is already shown here in the tabular form, that if you are aware of the two things, what is that? The number of protons in a given atom, and also the number of neutrons in the given atom. If you know, then it is fairly easy to estimate its spin, whether it is a zero or non-zero. Okay, if it is non-zero, whether it is integer or half integer. Okay, so those things can be estimated. How? Suppose if a nuclei possesses even number of protons or neutrons, such a nuclei is nuclear spin is said to be zero. Whatever the nuclei it may be, you can just directly come to a conclusion that if a atomic nuclei possess even number of neurons and even number of protons, then such a nuclei spin is zero. Therefore, it is inactive. Right? Therefore, it is inactive. And other nuclei, okay, what are the other possibilities? Well, okay, the protons and number of protons and number of neutrons can be, both of them can be odd number. In such a case, that the nuclear spin is going to be an integer number. In such a case, it is going to be an integer number. And then the other cases, like protons can be odd number, then neutrons can be even number, and the protons can be even number, or else the neutrons can be odd number. In both these cases, the nuclear spin is going to be half integer. Okay, it can be half, 3 by 2, 5 by 2, and so on. So therefore, you can just remember these table there, and then you will be able to answer the questions like which nuclei, if you are given a nuclei whether it is a NMR active or inactive, then you can make use of this table and answer quickly. Okay, just estimate the number of protons and neutrons. Okay, let us look at some of the common nuclei which are having half spin thing, like proton hydrogen 1. Okay, so it is said to be a proton nuclei. So in the hydrogen atom, in the nucleus, we have one proton. So we normally call hydrogen nucleus. Since we are talking about nucleus, we say it is a proton nucleus. Okay, so the proton is a half spin, right? Hydrogen nuclei possess half spin. Similarly, 13 carbon possess half spin. Similarly, 15 nitrogen possess half spin, right? And then 19 fluoride and 31 phosphorus. And these are some of the examples for magnetically active nuclei whose nuclear spin is half. The other one, let's say you take the example of 14 nitrogen or deuterium or boron 10. These are all the nuclei whose quantum number, whose nuclear quantum number is 1. Okay, so this is 1. And then inactive nuclei, NMR inactive nuclei are shown here. The best example is carbon 12 and then 16 oxygen. In both these cases, the number of protons and neutrons are basically, it is even number, and therefore the nuclei possess 0 spin. Therefore, it is NMR inactive. So this is very important thing as far as the NMR concept is concerned. So those nuclei which basically possess a spin, they are actually said to be NMR active. After all, the molecules contain the atoms, so we need to understand which are the nuclei magnetically active. So in NMR spectroscopy, we deal with at a given in a given experiment, we basically try to probe the magnetically active nuclei and their chemical environment. Okay, you know that the molecules are made up of atoms. At a given time, under given experimental condition, we will try to probe a given nuclei, a particular nuclei. This is nuclear properties of the elements, some of the important elements. If you are interested, you can go through it. Well, once the nucleus is having a spin, then naturally it will have an angular momentum. Naturally, it will have an angular momentum, and the length of or the magnitude of the angular momentum can be calculated by using a formula, the square root of I into I plus 1 multiplied by h cross. Please note that the h cross is outside. So using this formula, the length of the vector can be estimated. So the angular momentum of the nuclear spin is basically, you can represent in a vector notation, and the length of the vector, magnitude means it's a length of that nuclear spin you can represent in a vector, and the length of the vector is just the square root of 3 into I plus 1. Now, you know that still you can remember the quantum, I'm sure that still you remember the quantum chemistry, that we cannot simultaneously estimate different components of the angular momentum, right? That basically violates the Heisenberg uncertainty relation. So Lx and Ly simultaneously we cannot basically measure. Similarly, Ly and Lx or Lz and Lx. So these things basically we cannot, because they do not commute. If they commute, then it is possible to estimate. So what we have concluded in the quantum chemistry was like we can measure at a given time one of the components. That component, for the sake of convenience, we have taken it as like a Lz. Likewise, here also, if a nuclei is having a non-zero spin and it possesses the square root of I into I plus 1 multiplied by h cross is the magnitude of that angular momentum. Okay, please remember this is the nuclear angular momentum. And this nuclear angular momentum, you cannot basically measure exactly. Only you can length you can estimate, and also one of the component. That means the nuclear angular momentum will have 3 different components. Vector means it will have 3 different. along the x-axis, y-axis, and z-axis. However, we cannot determine all the nuclear angular momentum components. Only one of the components can be determined, and only that particular angular momentum component we take it for the sake of convenience along the z-axis. So mi h cross is the mh cross. This is what we have learned in the previous semester, and now you can just recall mi h cross is the z component of the nuclear angular momentum component. Okay, what is this? Z component of the nuclear angular momentum component. Only experimentally this can be measured. So the other components cannot be measured. Okay, so that is the thing. So when you do an experiment, you can only measure the one of the Z component of the nuclear angular momentum. So which actually depends upon the mi. What is this mi? Mi is the spin quantum number, nuclear spin quantum number. You know that based on the mi value, then it will have that much length. Okay, so mi value can vary from plus I to plus or minus I. That means I to I minus 1, and so on minus I. So it will have 2I plus 1 total orientations. It will have total 2I plus 1 orientations, starting from minus I to ending minus I. So it will have total 2I plus 1 orientations will be there. And these are some of the orientation that you can please recall and try to correlate with your the quantum chemistry class, the orbital angular momentum L. If it is half, it will have 2 orientations. If it is 1, it will have 3 different orientations. And if it is if L is equal to 2, then it will have 5 different orientations. Here, you just apply the same thing, but then you can consider only the nuclei. Well, this is the length of the one. So this will be, the vector length is basically nothing but square root of I into I plus 1 h cross. Okay, the length of the vector is this much. Now, one of the component, that is the z-axis, the nuclear, let's say the magnetic field is applied along the z-axis. In that case, that you can actually determine the z component, and this is the z component of the nuclear angular moment. And then it can also orient in another direction, that is the minus half. So the minus half, it will be pointing towards this direction, such that it will have the similar projection, whatever that the plus half is making. Okay, similar projection, so it will make it. Okay, so there are, based on the mi value, it can have different orientations. Okay, so all these vectors will have the identically same energy, but then they will process in the space differently. Okay, and then the next thing is that we can, the point what we have learned so far is that some of the atomic nuclei basically process the nuclear spin. Then if that is so, then they will have different orientations according to quantum mechanics. They will have different orientations in the external magnetic field. So we can do a small derivation, and we can calculate what is the energy of a atomic nuclei which is placed in external magnetic field. Why it is important? Because the NMR inherently, it is very weak, and we don't see the nuclear energy, and energy levels are basically split up into different energy levels. At a given temperature or at a room temperature, let's say, at room temperature, all these nuclear energy states are actually degenerate. That means they possess identically same energy. However, only when you place external magnetic field, they will split it into different energy levels. So, since the atomic nuclei, what we have learned so far, are basically said to be active, then such a nuclei behave like a basically bar magnet. Okay, and these bar magnets, if you place it in external magnetic field, how they behave and what is the energy level is something that I'm going to discuss with you. Okay, you can just remember in a shorthand cut short. In a cut short, what you remember is that atomic nuclei whose magnetic nuclear spin is non-zero, if you place an external magnetic field, how they behave. First of all, they are basically said to be a tiny bar magnets. Why? Because their nuclear spin is non-zero. Therefore, they will possess a non-zero the angular momentum. So angular momentum and the magnetic moment both are related. If you try to recollect basic electromagnetic theory, the angular momentum and basically the magnetic moment both are related. If some system is basically rotating, that will have a if a charged particle is rotating, that will have a angular that will have a magnetic moment. Likewise, here what we are discussing is some of the atomic nuclei possess the nuclear spin, and they behave like a tiny bar magnets. And such a tiny bar magnets, if you place it in external magnetic field, what happens? What is the energy of such a system? Okay, so the energy of a magnetic moment M, if you place an external magnetic field, it is basically is nothing but it is a scalar quantity, mu multiplied by b. Okay, the energy of the magnetic moment. Suppose they have a atomic nuclei, so we just learned that it can be considered as a tiny bar magnet, and it's a strength. The strength of the magnetic moment, the strength of the magnet can be determined by the magnetic moment. And then the energy, if you want to estimate such a nuclei when you place an external magnetic field, what will happen to its energy can be estimated by using this formula, that is E is equal to minus mu multiplied by B. Mu is the magnetic moment, okay, where B is the magnetic field strength, and generally we represent it in a Tesla, which is the SI unit. Of course, it can be expressed in terms of Gauss also, and 1 Tesla is equal to 10,000 Gauss. That is a convention. So please remember, some of the problems may be given in a Gauss, some of the problems can be given in a Tesla. So that time this conversion and all these things are important. Now, once you have the energy expression, a classical expression for the interaction energy of the bar magnet in an external magnetic field, that we can write down the Hamiltonian. The Hamiltonian is nothing but, H is equal to minus operator mu multiplied by B. Okay, so we can just convert that the classical expression into the quantum mechanical expression, and then this Hamiltonian, this particular Hamiltonian, you can allow it to operate upon suitable wave function, and then you can get the eigenvalues and multiply it by eigenfunction back. Okay, so that we can do it. Of course, we will not go to those details, but then we will try to understand very basics of what is the energy of nuclear energy states. The nuclear energy states are basically, or directly you can take it from here itself. So the Hamiltonian is given by this expression, and later, but we know that the magnetic moment, the expression for magnetic moment is given by gamma I bar, gamma operator I, gamma multiplied by operator I. What is gamma? Actually, so the magnetic moment is basically, previously we have already discussed that the magnetic moment and the angular momentum of a system both are related. Okay, so if a system is rotating, that will have an angular momentum, and if it is having an angular momentum, definitely it will behave like a magnet. It will behave like a bar magnet. Okay, now mu is equal to gamma I, right? So in this Hamiltonian expression, you can just replace mu is equal to gamma I, and then the Hamiltonian is equal to minus gamma I, operator I multiplied by B. Okay, what is this negative sign? Negative sign is that the interaction energy is basically opposing the applied magnetic field direction. Okay, if you apply this direction, the magnetic field, the interaction energy of the bar magnet which you are considering, that will be in the opposite direction. So just to address that particular aspect, so the negative sign has been introduced in the expression. So this is a simple, straightforward Hamiltonian expression of an atomic nuclei whose spin is non-zero, and if it keeps such a atomic nuclei in presence of an external magnetic field strength of B, then it will have that much. That is the Hamiltonian operator. So once you have this operator, then you can do you can follow the quantum solving the quantum mechanics problem. Like you can write down the Schrodinger wave equation. Then you solve the time independent Schrodinger wave equation, and then you can get the eigenvalues. So here the eigenvalues are, since the operator actually related to the atomic spin, atomic nucleus spin, you can see that what is I? I is the atomic nucleus spin. Hamiltonian is expressed in terms of nucleus spin. Of course, this is a constant at a given magnetic field. This is a constant, and the this is gamma is called gyromagnetic ratio or gyro or magnetogyric ratio, which is nothing but it is a ratio of magnetic moment versus the angular momentum, magnetic moment versus the angular momentum ratio. We will come to that point later, but you can remember that the Hamiltonian is nothing but minus gamma operator I multiplied by B. It depends upon these quantities. So once you have this Hamiltonian, you can always substitute this Hamiltonian in the Schrodinger wave equation of the system and then try to solve it. We will not do that, but then straight away you can just take it from the what has been solved, and then we'll try to proceed from this expression onwards. So the energy expression or the eigenvalue expression is given by E mi is equal to gamma h cross I B0. What is B0? B0 is nothing but the external magnetic field which you are actually applying, where you are basically keeping your atomic nuclei. Okay, that is the expression. I mean, and then the rest of the things are actually remain same. So what is this expression? The energy of the nuclei, if you keep it in external magnetic field, and whose magnetic field is basically applied in a particular direction, that is one particular z direction, and its energy is going to be that much. But please remember that what is I? So I here, it's not a single number. The possible values of I is basically 2i plus 1. The possible values for I is basically 2i plus 1. And then it can start from minus I minus 1, I minus 2, and so on, and then it will go up to minus I. So it will have so many values. It doesn't have one value. So depending upon the I value, you can have different energy levels. Okay, if it is having only one, if I is equal to 0, then the interaction energy is 0. Simply you can just take it, you can understand the other way also. Suppose if there is no spin, if the spin quantum number is 0, the nuclear spin quantum number of, let's say, the carbon 12, if you take it, if the quantum number is 0, therefore there is no interaction energy, and then simply it is 0. Suppose if I is non-zero, let's say if it is half. If I is half, then it will also have minus half also. I cannot be only one particular value. If it is non-zero, definitely it will have, starting from minus I to plus I, it will have so many values, depending upon the I value. So accordingly, we will have different possible energy states. That's the point I want to say. The take-home message from all this discussion is very simple. So certain nuclei possess the spin, and then because of the spin, they behave like a tiny bar magnets. And then the energy, if you place such a nuclei in the external magnetic field, then the energy expression is given by minus gamma h cross I B0. Okay, if I is half, okay, let's say if I is half, then it can have the values of plus or minus I. It can have the values of plus or minus I. That means the energy can be half gamma h cross B0 and minus half gamma h cross B0. There are three different values are possible. Similarly, you can substitute different values for I, and then accordingly you can have it. This previous expression you can see. So what is the energy of this system and what is the energy of this particular orientation? If you want to know, that is possible, you can substitute I, what is the value of I in this particular expression, and accordingly we can have different energy levels. Okay. And then the magnetic moment of nucleus, sometimes we express in terms of the nuclear G factor, Gi, G suffix I. The nuclear Z factor is is basically a characteristic of a nucleus, and the Bohr magneton or the nuclear magneton. Like the Bohr magneton is nothing but the electron quantities. For electron, we say it is a Bohr magneton. Similarly, we can have the nuclear magneton as well, and gamma H cross is equal to Ga mu n. That is the another relation which is helpful for understanding the NMR spectroscopy. And this gamma and G, gamma is the gyromagnetic ratio or magnetogyric ratio. Both are okay. Both terminals are okay. And this G factor, both are basically related. And then this gamma is something that very, very important as far as the Larmor frequencies of the nucleus is concerned. We'll see that thing very in a minute. And then, and G factors are also important in nuclear thing. Since we mostly deal with, in a given experiment, since we only deal with one particular nuclei, these quantities we don't really pay any attention. But then indirectly, basically, these quantities are very much important to us. Okay, since in a actual experiment actual experiment is done at a given instant, we record the NMR spectrum of a particular nuclei. Therefore, all these things are fixed. Let's say if a proton, if you consider its a gyromagnetic ratio is fixed and G factor, and then all these Bohr magnets, everything is fixed. Therefore, normally we don't consider and pay much attention, but these are the ones actually influence the Larmor frequencies. Therefore, we have to pay attention. And also, the gamma is the gyromagnetic ratio or the magnetogyric ratio, which actually determines the orientation of rotation. When you place the external, when you place a non-zero spinning nuclei in the external magnetic field, now the question is that how it is rotating. How it is rotating, that is actually decided by the gamma of that particular nuclei. Okay, if gamma is positive or if gamma is negative, accordingly you can have different energy levels. Okay, if gamma is positive, typically is the case for most of the nuclei, but gamma can also be negative. In such a case, the energy levels orientation will be different. For example, if, as I pointed out already, most of the nucleus it is positive gamma. If it is positive, then the negative energy state will be down, whereas the positive energy state will be in the higher side. So that is the thing. So the gamma is not only determines the Larmor frequency, but also it dictates the orientation of the energy levels. Whether it is the negative one has to be in the below or the positive one has to be in the below, that is decided with the gamma itself. Okay, if you consider proton, its a gamma is 26 point something, it's 26.75 thing quantity, and then since it is a positive, so the minus energy state will be pointing will be placed in the bottom level, and then positive state will be kept in the upper state. Suppose if it is negative, then it will be reversed. Why? Because just now we have seen already in the expression that the interaction energy of the magnetic moment is given by minus gamma H cross I B0. If gamma is already negative minus that is negative, and then there is a negative sign, both cancel out, and then in such a situation, the positive one will be lower and then negative one will be higher, right? So likewise. Now, with this background, let us try to understand what is Larmor frequency and the resonance condition in the NMR spectroscopy. Now, we understood from the previous discussion that certain nuclei possess nuclear spin, and then if you place them in external magnetic fields, their energy states will be split into several, which is actually decided by the spin quantum number I. The NMR spectroscopy, what we study in the academics and also what we practice in the research, mostly it deals with the half spinning nuclei. Mostly deals with the half spin nuclei. The quadrupole spinning nuclei are there, like nitrogen and then this deuterium, all these things are there, but still those spectroscopy, those NMR spectroscopy were not established much, and then there is less information from that side, because as you can see here, if there is a, if the spin quantum number is half, then you can expect two quantum state, nucleus quantum states, right? That means you have the below one energy level and then upper one energy level. There are two energy statements, that 1 and 2, right? One you can kept up and the other one kept below. Now, how many transitions are possible between these two states? Definitely there is only one transition is possible, right? Therefore, this spectroscopy is much simpler. On the other hand, suppose you consider a nuclei whose quantum number is 1. If the spin quantum number is 1, there can be three possible orientations. That means there can be three different transitions also. You may please recall the image what we have seen here. Let's say these are three different orientations. What are these? This is one orientation. If the spin quantum number I is 1, this is one orientation, this is another orientation, this is another orientation. Now, how many transitions are there? Well, if you consider this as a ground state and this is a middle state, right? This transition is possible. And similarly, from here to here, one transition is possible. Similarly, there is another transition is possible, right? There are three different transitions are possible. Therefore, such a spectroscopy is going to be much complex, isn't it? That is why, and moreover, we don't get much information out of this, but for our normal usage and to access some of the information, this half spin nuclei is more than sufficient. Okay, so most of the cases in MSc level, we only talk about half spin NMR spectroscopy, right? It doesn't mean that other spinning nuclei NMR spectroscopy is not possible. Well, it is indeed possible, but then we don't pay any attention. Okay, even in research also, mostly we deal with half spinning NMR spectroscopy because that is enough for our understanding. Okay, if there is a need and necessity, definitely we can explore that one. As of now, it was not explored because there is a less practical usage in that particular direction. So, my discussion from here on, mostly it will be half spin nuclei. Okay, now we already understood that the energy levels, the nuclear energy levels, the energy of a nuclear energy can be estimated based on the previous equation, that is EMI is equal to minus gamma H cross I B0. If it is half, there can be, so half and then minus half. Two things you can substitute, and then the energy of the two states can be written, right? Now the thing is that if I ask you to estimate what is the energy difference between these two states, for example, so the one state, if you substitute half, if you substitute minus half, then it is going to be positive. So for a half spin nuclei, I is equal to half, or it can be minus half also. There are two spin orientations are possible for nucleus, for a half spin nuclei, and then it is like E minus half and then E plus half. The energy difference, if I ask you to calculate, it is already given. Delta E is nothing but minus E minus, sorry, E minus half minus E plus half. Why? Because E minus half, please remember that. Why you are taking only E minus half first? Because this is upper, this is higher in energy. Please remember the previous expression that if you substitute minus half, then there is already there is a negative sign, so that energy will be higher in energy. That nuclear energy will be higher in energy. And then if you substitute positive, then that energy will be negative. So therefore, when you ask basically to calculate what is the energy difference always the higher energy minus lower energy state. That is what it is done here. So it is half gamma H cross B0 minus, and there is a minus half gamma H cross so and so. Now, if you combine these things, basically there is a minus half and then there is a minus sign, and there is a minus sign here. So both together it is a positive sign, plus half, and then there is another plus half over here. Then the energy difference between the two nuclear spinning states is given by gamma h cross b0. Gamma h cross b0. This is very, very important expression. So the delta E is what? The delta E is the energy difference between the nuclear spinning spin states. Okay, it is given by gamma h cross b0. Okay, now this expression, what is shown here, that okay, if when this energy splitting happens, please don't forget this. The energy splitting you can see only when if you place the nuclei in the external magnetic field. Otherwise, what happens? They will be degenerate. Otherwise, they will be degenerate. That means they will possess all these half spin nuclei. We were talking about the two states. The two states discussion comes into the picture only when the applied magnetic field is non-zero. If it is zero, both will be like this. That is exactly happens here. Suppose if you have a hydrogen here, hydrogen gas is everywhere it is there, then it's a spin, even though it has the non-zero spin, since there is no magnet here, so its nuclear spin energy levels will be degenerate. That means they will have identically same energy. When do you see these splitting? The splitting is only possible when you place the hydrogen atoms in the external magnetic field. Otherwise, you will see only particular single state. Okay. Now, this energy gap is something that we have estimated here. Okay. So when you place in the external magnetic field, there is a splitting. Now, the splitting is gamma h cross b0. Now, once you have this energy difference, now we know that we have different electromagnetic radiations, the electromagnetic spectrum. So we have different, starting from the radio waves, then we have the microwaves, we have the IR infrared rays, and then we have visible ultraviolet, X-rays, and gamma rays. So this is a sequence. Okay, so based on the energy I just spelled out. So the gamma rays will have the highest energy, whereas the radio waves have the very lowest energy in terms of energy, of course. Now, this energy gap, if you can shine externally some radiation which is matching with this energy gaps of atomic nuclei, then we can actually explore a new spectroscopy, and which was the original thought of developing this actually NMR spectroscopy. Okay, so once you have the energy gap splitting between the energy levels, of course you can also calculate the energy difference between the electronic states. Why not the vibrational energy state? Of course, rotational energy state, many energy states are possible. The energy differences can be calculated in a similar fashion by following a little bit of quantum mechanics. And then once we have the energy gaps, then we can look into the appropriate electromagnetic radiation, that we have so many different type of radiations are there. So you can just try to pick up such a the electromagnetic radiation, and then you just shine that radiation on the nuclei. On that particular system, then the transitions are possible, and try to observe by recording those transitions, try to interpret try to extract some information. So that is the basic fundamental aspect of spectroscopy. Similar is the case for NMR spectroscopy. So why we are deriving a energy gap expression? Why? Well, because if you understand the energy differences between the nuclear energy states, then it is possible to exactly locate which radiation that we can use it for this spectroscopy. That is the purpose. So it is already done, so we don't have to break our head. So the energy gaps of any atomic nuclei that you may take it, they are basically of the order of a few megahertz. So therefore, it is thought that radio waves are appropriate for making transition between their nuclear energy states. And then So in the NMR spectroscopy, that people use the radio waves. Why? Because the atomic nuclear energy state differences, the energy difference between the different energy levels of any atomic nuclei that you may think of, usually and typically they fall in the radio waves region. Therefore, we use radio waves to make it to have the transition, and therefore to see the appropriate corresponding peaks. Okay, so from this particular thing, we can actually derive a simple expression for the frequency. One here you have the delta E. When this delta E is matching with the external radio, uh, external magnetic field, electromagnetic field, that is the radio waves. I already given the answer. Then it is possible that we can have a resonance condition. Okay, so we have the energy gap of this means, and then if you use that radiation which is exactly matching with this energy gap, then we have the spectroscopy. So that is, in order to have the frequency condition, that you can substitute here, there is a h mu. H mu is equal to delta E. Then the delta E is nothing but the energy gap. If that is matching with the h nu of h nu is nothing but the incident photon, that photon is nothing but the radio frequency photon. So if the radio frequency is supplied, then we have the resonant condition. Therefore, that h nu is equal to gamma h cross b0. Gamma h cross b0. H cross, if you try to basically expand it, that is nothing but h. Basically, we have a delta E. This is the expression. Delta E is equal to gamma h cross b0. Okay, now this, if this is equal to h nu, that is the photon energy, then we have the resonant condition. So gamma h, I will write it by h cross, I will write it by h by 2 pi, and then b0. Okay, this h and this h both cancel out, and you have mu is equal to gamma b0 by 2 pi. Gamma mu 0 by 2 pi. Okay, so this frequency has a special notation, that is L. L stands for Larmor frequency. L stands for Larmor frequency. Now what happens? The next thing what happens is that, okay, when you place a non-zero nuclei, atomic nuclei in an external magnetic field, especially the half-spin nuclei, then what happens is that there is a resonance condition. Okay, there is a resonance condition, and when you supply appropriate radiation, then we'll have a resonance condition, and then the NMR spectroscopy is something that we will probe at what frequency this particular nucleus is basically rotating. So by probing these frequencies, we can estimate the characteristic of atomic nuclei where they have present in a given molecule. Okay, so before that, Larmor frequency is nothing but is given by this equation. Mu L is equal to gamma B0 by 2 pi. This is very, very important expression. Okay, that means when you keep a magnetic non-zero spinning nuclei, so non-zero spin nuclei in an external magnetic field, it will precess, basically, it will precess at that particular frequency. What is that? This is the frequency. Okay, so the moment you keep it in external magnetic field, then it will basically precess. What is that precessional frequency, precessional motion? These are really related. I'm sure that most of you have played with spinning tops in your childhood. So the precessional motion is nothing but the spinning top motion. So the rotational axis of a spinning top is keep on changing. You might have noticed that when you when it starts rotating, initially it will be straight, but then afterwards it's still rotating, but then it will be bending. Okay, initially it will be straight, it is rotating like this, but then later on it will be still rotating, but then in this direction. After some time it will be in this direction. So that particular So with respect to time, basically the rotational axis is basically changing. So therefore they use a special term, is the precessional motion, spinning top motion, or the gyroscope motion. Okay. So the take-home message is this. So when you place a non-zero atomic nuclei in an external magnetic field which is non-zero, then basically it precesses with a certain frequency, and whose frequency is given by Larmor frequency. That Larmor frequency is equal to gamma b0 by h cross. Okay, gamma b0 by h cross. Now the NMR spectroscopy is all about measuring this precessional motion of different nuclei in a given molecule. So the precessional motions of atomic nuclei. Let's say if it is a half spin, and if you are talking about protons, so in a proton NMR spectroscopy, we try to estimate and measure the precessional frequencies of protons located in different chemical environment of the molecule. You have ethanol. Just what I said was that ethanol molecule, you have still proton, that is CH3 there is a proton, CH2 there is a proton, and OH there is a proton. All these protons are not same. They are different. They are protons. To talk about, we represent only with the H, but then their chemical environment is something it is different. Therefore, their precessional frequencies will be different. We'll come to that point later. So the NMR spectroscopy is all about measuring the precessional frequency of the atomic nuclei which you are interested in a given experiment, and then their postmortem, and then later on we'll try to postmortem what exactly is happening based on the data. Okay, so that is important. Now, the precessional motion of atomic nuclei depends upon two things. What are those? In the expression, it is straightforward. One is the gyromagnetic ratio, or magnetic gyro ratio, that is gamma. The other one is the external field strength. The other one is the external field strength. So, as you can see here, it is very straightforward. If you have a nuclei with a high gyromagnetic ratio, then definitely its precessional frequency will be high, isn't it? So as from the equation, I'm not talking about something new. So from the equation, you can see it is directly proportional to, it is in the numerator. If you want to increase the frequency, then you have to increase the gamma. So that means if you have a nuclei which is having high gyromagnetic ratio, such a nuclei will be precessing at higher frequencies. Similarly, if you place it in an external magnetic field, if you place atomic nuclei in a smaller magnetic field strength and then higher magnetic field strength, I mean, in terms of numbers, let's say 1 Tesla, 2 Tesla, and then 10 Tesla. So the one which is placed in a 10 Tesla, that nuclei will precess at higher. Please remember that in all cases, you have to keep the same nuclei. Of course, if you change the nuclei, the gyromagnetic ratio will be different. Please remember that the gyromagnetic ratio, it is E by M. Okay, E by M. That the M is the mass of the thing, mass of the proton. So the proton is, the mass is relatively small as compared to the other nuclei. For example, carbon-13. The carbon-13 atomic mass is very, very high as compared to a proton. Proton is roughly 1 unit, and then carbon is 12. So therefore, its gyromagnetic ratios other than protons, they will have very high, very low gyromagnetic ratio. You can see here the table. In the table, the proton has gyromagnetic ratio of 26.75 into multiplied by 10 raised to 7 per Tesla per second. Per Tesla per second. That is the quantity of the gyromagnetic ratio of proton. We just go to the next one. The next one is the deuterium. Deuterium, its spin is 1, and its gyromagnetic ratio is 4. Carbon-13, you go there. Carbon-13 and proton both you try to match up, and then you have the 6.73. So nitrogen, so it is even still smaller. It is 1.93. So the Larmor frequencies of the atomic nuclei which is placed in external magnetic field is different, and it is decided by the two factors. One is the gyromagnetic ratio, and other one is the external magnetic field strength. Okay, if you increase the magnetic field strength, the Fresnel frequency increases, and if you decrease it, it will decreases. If a nuclei is having high gyromagnetic ratio, whose frequencies will be higher. Okay, whose frequencies will be higher. Okay, that is the one thing. And then the Fresnel, estimating the Fresnel frequencies of the atomic nucleus is very important. And for your kind information, and just for small statistics, that if you keep a proton nucleus, a proton in a external magnetic field strength of 1 Tesla. So what would be its Larmor frequency? Well, you can estimate by using that formula, but roughly I can say that it will precess at 40 megahertz. It will precess at 40 megahertz. Okay. And in this diagram, it is shown here that I already pointed out this point that when there is no external magnetic field, the half-spin nuclei process degenerate energy levels. What are these energy levels? Nucleus spin energy states. The nucleus energy levels are identical, generate, but the moment you place it in external magnetic field, they will actually split up into two different possibilities. And then the plus half, normally we represent with a alpha state. Alpha state will be below, and then minus half, that is beta state, it will be the higher thing. What I wanted is that let us try to estimate the Fresnel frequencies of certain nuclei placed in external magnetic field strength. So what I request all of you, just take a piece of pen and try to work out this formula. Try to work out this particular problem. What is the energy difference between two spin states of proton in magnetic field strength of 5.87 Tesla and 13 carbon in the same magnetic field? What is the energy difference between two spin states of proton when you place it in an external magnetic field strength of 5.87 Tesla? That is one problem. Similarly, in the same field separately in the next experiment, if you place it in a if you place 13 carbon, so what will be the energy difference? How do you estimate the energy difference? What is the formula should be used here?
Gamma H cross B0.
Can you just estimate and give me the answer? What is gamma? Gamma is 26.75 multiplied by 10 raised to 7 per Tesla per second. That is the proton, isn't it? So you can use that. What is H cross? H by 2 pi. Okay, H is nothing but 6.625 into 10 raised to minus 27 or 37 or 34.
34 minus 34.
Okay, so what is the answer then? Final answer. Pi is 3.14. 2 multiplied by 3.142. So you can estimate the value. So it is like this. I already given the answer. So the gamma H cross B0 is the energy difference as per our discussion, and you can straight away calculate. So everything is known. There is nothing is indirect. This is a direct problem. For proton, in one case, the energy difference you have to estimate. For the carbon 13, in the other case, you have to estimate. So it is 26.75 is the gamma value of the proton. So it is straight away taken. Okay, and then this is the 6.625. This is the Planck constant, and then B is the Tesla. It's already given in Tesla. And if it is not given in Tesla, so you convert the Gauss into Tesla and then do the exercise. And then B is the 5.87. It is taken from the problem. And this pi value 2 into and then pi is 3.14, or you can it was taken. So the energy difference is how much? Delta is equal to 1.66 into 10 raised to minus 27 joules. That is for the proton. And for the carbon 13, if you try to estimate, the energy difference is how much? 4.18 into 10 raised to minus 26 joules. So what is the difference between these two? Why the energy gap of 13 carbon is much smaller than the proton nucleus because of the gamma. So gamma is smaller in the case of 13 carbon. 13 carbon, it is 6.72. Whereas in the case of proton, right, this is the number actually is the difference between the proton and then 13 carbon. The gamma of carbon 13 is almost 4 times smaller than the gamma of the hydrogen nucleus. Therefore, that reflected in the energy gap. Okay, so it's such a, you can see, forget about this number, what is there, because when you have a huge number, this is the huge number. So, I mean, this is very small number. 10 raised to minus 25, 20, and minus 26. This is very, very small. So that means is what? That means that the energy gap is very, very small. Even if you apply that 5.87 Tesla, such a huge magnet, even if you place it in such a huge magnetic field, then even then the energy difference between the two nuclear spin states of a proton or maybe 13 carbon is still, it is smaller. That is the reason why actually this is said to be, it's not a sensitive technique. Inherently, it is not a sensitive technique. What do I mean by sensitive technique? Well, in the spectroscopy, certain techniques are said to be sensitive. Means even for a small changes that we see a larger differences or variation in the spectrum, which is actually good that you can interpret very nicely. But then there are techniques like this NMR spectroscopy, that inherently you can see that the energy gap is very, very small, as a result of which the population difference is very small. Any spectroscopy technique, that if we have a huge difference in population between the ground state and then excited state, then we can have accordingly we can have the different transitions, and then that basically tells you whether it is a sensitive or insensitive. So NMR is concerned that since the energy
Sir,
levels are very close, yeah,
sir,
yes,
if gamma value is changed, how energy gap will changes? How it's depend on gamma value?
gamma actually E by M. Please remember gamma, the fundamental relation, how to calculate gamma of a nucleus or anything, it can be calculated E by 2M. What is M? M is the mass of that particular thing, nuclei, right? For proton,
Yes,
it is M is 1 point something, okay? Whereas
yes,
for the case of 13 carbon, M is very high. Something which is increasing in the denominator part, naturally the gamma will be reduced, right?
yes, right. So now I understand.
That is the reason why that carbon and then carbon is basically heavier as compared to the proton. Heavier nucleus. So heavier nuclei will have a smaller gamma values, and lighter nuclei will have a higher gamma value. That is the
So
fundamental thumb rule.
yeah, it's inversely proportional
Okay.
to mass of the element.
Yes, exactly. So that is the reason why that the energy gap, even then also, even then, even if you keep such a huge magnetic field, these nuclei energy state difference is basically very, very small. And as a result of which, what happens is that then you will see a equal population distribution from the ground nuclear energy state and the excited energy state. And therefore, the population difference is very, very small, and that is actually lead to the concept of insensitivity to the insensitivity. Okay, so if any spectroscopic technique is said to be sensitive, then it's the population difference between the ground and excited state should be sufficiently large so that the transitions will be more, and then we will see a good spectrum out of which. But as far as the NMR is concerned, the energy gap, if you basically convert all these numbers into calories, the energy, nuclear energy difference of half spin nuclei is roughly about 1 calorie, 0.1 calorie, 0.1 calorie. So what is the thermal energy at room temperature? Thermal energy means that because of the system, the position of the system at a given temperature, it will possess some energy. For example, we are in a room temperature of maybe let's say 20 or 25 degrees centigrade. So what is the energy? So roughly it is 2 calories. Okay. So then the nuclear energy state, if you convert these numbers into calories, it is going to be roughly about 0.1 calorie. So energy gap is even very, very smaller. That is the reason why that the population, I mean the nuclei, will try to arrange in both the states, as a result of which it will lead to equal population distribution among the ground nuclear energy state and then excited energy state. Okay, as a result of which that the technique is going to be insensitive. Okay, we will come to that maybe in the next class.